right, hello. So this is section 1.7. In this section, we're going to talk more about vectors. Um, so I want to start off with a vector equation that should look fairly familiar given what we've talked about, especially in section 1.5, and sort of a standard question to ask when I'm given a set of vectors. So let's say I had the following three vectors, 5, 0, 0, 7, 2, negative 6, and 9, 4, 8. And I wanted to know if this vector equation has a non-trivial solution. And so remember, in the context of a homogeneous equation like this, where I'm trying to solve for the 0 vector, a non-trivial solution would be some assignment of x1, x2, and x3, such that at least one of these three variables is non-zero. Of course, if you look at the vectors, you'd have to have at least two of them be non-zero for this to be true. And then, if it's a non-trivial, if there is no non-trivial solution, then there's only the trivial solution, where x1, x2, and x3 are all 0. So, in section 1.5, we talked about how to solve this, of course, when we have a matrix equation, ax equals b. But remember, we can solve any vector equation by just turning it into a matrix equation, where the columns of my matrix A are just the vectors. So we know how to solve this question, and we know how to answer it, but in the context of talking about vectors, and so remember, sort of especially early on in linear algebra, we end up talking about the same problem sort of in multiple different contexts, right? So we might talk about this problem of solving a homogeneous equation in the context of matrices, and this section we're going to talk about it in the context of vectors. And so technique-wise, in terms of solving these problems, there's not going to be a whole lot of new techniques introduced, just some new definitions for when we're talking about this problem more in the context of vectors. And I think there's some reasons behind that. And, well, specifically with vectors, I think there are reasons behind that because we will talk about vectors a lot more, especially in some of the later sections, like when we talk about vector spaces and things like that. And so if I have a set of vectors like this that only has the trivial solution, that is, if this equation only has the trivial solution, so the only assignment of variables that will make this true are all 0, this set of vectors has a special name, and this is just one example of a type of equation, but of course this can generalize to any number of vectors in any dimension, right? So these vectors are all in R3 because they're vectors of length 3, but we could generalize this to vectors of Rn, and that's what the definition will do. All right, so if this equation, or the more general version of this equation where I have p vectors in Rn, only has the trivial solution, then we say that the p vectors, v1 through vp, are linearly independent. So that is the only set of variables that will make this equation true, is if each one of these x terms is equal to 0. And so if I have a set of vectors that are not linearly independent, that is, there is some non-trivial solution to this equation, then we say that the set of vectors is linearly dependent. And so that is, if they are linearly dependent, of course, there is a non-trivial solution. All right. So I left this little box here because I want to give some intuition as to why we choose these definitions. I think these, when I think about these definitions and I think about sort of my intuition behind them, it helps me to remember what they're talking about and sort of why we chose them, and why, especially moving forward, we might care about linearly independent and linearly dependent sets of vectors. And we'll talk about that more certainly later in the course. But suppose we actually did have constants. So let's say we had three vectors, v1, v2, and v3, and non-zero constants c1, c2, and c3, such that so let's say we had this going on where I have these three vectors and three constants not equal to 0, such that this was true, right? So of course this means, as the definition here states, that these three vectors are linearly dependent. And basically, the way I like to think about this is this equation being true and these c's being non-zero implies that any one of these three vectors can be written as a linear combination of the other two. So as an example, let's say I wanted to solve this equation for v1. Well, I could just subtract this and then divide by negative c1, right? And I would get that negative c2 over c1 times v2 plus negative c3 over v3 times v3 over c1. I'll bring the c to specify. Right, I can rearrange this top equation to get this equation. And so notice what this equation implies is that I can actually write, again, v1 as this linear combination of v2 and v3. And so in that way, I kind of think of the vectors as not being independent from one another. That is, like, v1 can sort of be constructed from v2 and v3. So, like, what we'll eventually talk about is how we can sort of reach every vector, say, in R3 using the smallest set of vectors, right? Remember, if we can reach every vector in R3 using some linear combination of a set of vectors, then we say that set of vectors spans R3. And so what this tells me is that v1 is in the span of v2 and v3, right? Because v1 can be written as a linear combination of the two. And so that means v1 isn't independent from these two vectors. It's sort of, you can reach v1 from v2 and v3. And so notice, in this way, I could have solved this equation for either one of these three vectors, and so any one of these vectors is in the span of the other two. And so that's to say that this set is linearly dependent. Of course, if the set is linearly independent, then the only thing that makes this equation true are c1, c2, c3 equals 0. And so that would mean that none of these vectors is in the span of the other two. And so all of these vectors in that way are sort of independent from one another. And so that's sort of intuition, at least on my end, behind why we give these definitions. So linearly independent, this only has a trivial solution. Also, no single vector is in the span of the other p minus 1. Linearly dependent, this has some non-trivial solution, and we can find something like this, where at least one of the vectors is in the span of some of a smaller subset of the other vectors. All right, and so after introducing this, I figured we could just reword this equation, or reword this question, and solve it. So let's see. Keep these vectors in mind. We're going to use the same vectors, but we're going to rephrase this question. And all we're going to do, we're going to ask the exact same question, but we're going to rephrase it in terms of these two definitions. So here's our new standard vector question. Are the vectors, and I've already forgotten what the vectors were, of course, 5, 0, 0, 7, 2, negative 6, and 4, -8. Linearly independent. And so we know now that this question is exactly the same as the question I asked before. Are these vectors linearly dependent? Just does the homogeneous system corresponding to these vectors have a non-trivial solution? And we know how to solve that, so let's do some row reduction. So I remember teaching this class in the spring. When we were studying for the first test, sorry, I actually can't. I have a hard time writing and talking at the same time, so I'll tell my story here. So when I was we were talking about ways to strategies for the first test, and so I think one of the hard parts, especially early on with linear algebra, is that again, like, you get asked the same question but like very multiple different ways. So right, like, it turns out that this question is the exact same question as basically what we did in section 1.5 with homogeneous solutions to equations. And so I remember I was like, well, of course, like on a written test where it's a little easier to give partial credit, it's like, well, if all else fails, just row reduce a matrix, and you've probably done most of the work. And then from there, it's sort of just deciphering, okay, I got this matrix, how do I interpret it? And so you'll notice, like, especially early on, like a description of linear algebra can just be like, how many ways can we think of to interpret a row reduced matrix? So I wrote the augmented matrix here, but as I was doing that, I remembered that I wanted to notice something. So notice that all we're looking for here is a non-trivial solution in this augmented matrix, right? And so a non-trivial solution happens when we get a free variable, and that is a variable that does not correspond to a leading one or a pivot column. But we actually don't need this last column of zeros to know if we're going to get that, right? All we need to count are the number of leading ones in the reduced row echelon form matrix and ask, does that equal the number of variables, which in this case it's 3 because there are 3 vectors. And so if we have as many leading ones as we do vectors, there will not be a non-trivial solution. And so we actually don't even need the augmented matrix for this. I don't know why I erased the whole thing. We just need the coefficient matrix whose columns are these 3 vectors. And so this doesn't really change anything, remember, because all of our row operations anyways are going to, all of the row operations we do anyways are going to leave that last column alone of all zeros. It just sort of saves us some writing. So anyways, let's row reduce this. This 5 is already sort of good, nothing non-zero below it. I'm not going to divide through yet. I am going to start with 1/2 row 2. Yeah, that's good. Does that look right to everyone? Yeah, I think that's right. Okay, so now we're going to do 1/4 row 3. 0, 1, 2, 0, 0, 1. And now we want to just start working our way back up. So I'll do this a little quicker since at this point it's not horrible. We're just going to use this leading one here to eliminate the 9 and the 2, and so that'll be -2 row 3 plus row 2, and -9 row 3 plus row 1. And then we only have two more steps remaining, but I'll do them actually at the same time. So negative 7 row 2 plus row 1. Notice that this step gets rid of that 7, and so I just have a 5 left. And so after that, I'm going to do 1/5 row 1. And we get the following row-reduced matrix. And so notice this matrix has 3 leading ones. If we translate this back to a system of equations, remember the last column here, one reason we don't need it for this is because, remember, the last column is just going to be all zeros this entire time. And so this corresponds to this assignment of variables. And so remember that this means that the homogeneous equation defined by these 3 vectors, which I had talked about was sort of the original way of phrasing this question, only has the trivial solution. And so this set of vectors is linearly independent. So to answer this question, yes. This set of vectors is linearly independent because the homogeneous equation only has the trivial solution. Another way of putting it, and I think this was a theorem mentioned, notice we have 3 vectors and 3 leading ones or 3 pivot variables in our row-reduced echelon form matrix. And so if there are equal number of pivot variables and vectors, then we also have only the trivial solution. Because again, this corresponds to each of these variables being fixed. All right. So we've got a little more I want to do this video. So this might run a little on the longer side, but there wasn't a great way to sort of break this up any other way. So notice what we did to solve this. So I'm going to erase the work for now, since this was just row-reduced matrix work, but I'm going to leave up, maybe I'll leave up the end and the beginning. So notice what we did here. We just solved the matrix equation AX equals 0, right, if this is our matrix A. Right, so if this is matrix A, we actually just solved this. And again, this is what I was saying, is that this very much corresponds to what we did in section 1.5. And so we just made these vectors the columns of this matrix A, solved this, and showed that this only had the trivial solution. So and so this means we can also talk about the columns of a matrix A being linearly independent or linearly dependent. And what this shows is that we actually know exactly when the specific column vectors of a matrix A will be linearly dependent or independent. So we'll call this fact. So remember, this is a way of defining matrix A based on its columns. So suppose this is our matrix A, and its columns are A1 through AP. Then the vectors A1 through AP are linearly independent if and only if AX equals 0 has only the trivial solution. So this is sort of just stating what we've sort of brought together so far, sort of bringing together what we learned in section 1.5 and 1.7, that the columns of a matrix A, when thought of as vectors, and I like to sort of think of it as like separating the columns out into separate vectors. This set of vectors is linearly independent if and only if this matrix equation only has the trivial solution, which is what we showed here. And so this sort of shows a nice back and forth between these vector equations and matrix equations, where we solve the vector equations by turning these vectors into a matrix and using our row reduction tools to solve. But we can also think of matrix equations sort of as vector equations by considering the columns of a matrix as individual vectors. So this means we can answer questions like this, and this will actually be our last example for the video. So we're given this matrix A, and we want to determine if the columns of A are linearly independent. Well, we know from this fact that all we want to do is row reduce this matrix, look at the number of pivots compared to the number of columns. So there are 3 columns. If we row reduce, we should get 3 pivots, and that will answer our question. And so let's finish with some row reducing. So 2 row 1 plus row 3 to replace row 3. Sorry, I think I wanted to do this. So I'm going to change this problem up just a little bit. We're going to make this 2 and negative 2. So we're going to take this matrix A, and we want to determine if the columns of A are linearly independent. And so this gives us that. So we still have the first step. Notice we've got a negative 2 here, negative 2 there, and we want to determine if these columns are linearly independent. I'll explain at the end why I want that to be a negative 2 instead of a positive 2. But after this first step, notice this 3 is now going to be a pivot, so we're going to do negative row 2 plus row 3. And so now we want to divide row 2 by 3. And finally, we want to do 2 row 2 plus row 1. And so notice here, so I chose this because I wanted to look at an example of what it looks like when we get something that's not linearly independent. And so notice here, after this row reducing, we get only 2 pivot variables, right? X1 and X2, and X3 is free. So since only 2 leading ones, that is X3 is free, the columns of A are not linearly independent. They are linearly dependent. So this is what it looks like when we get linearly dependent. However, if we'd had 3 leading ones, they would have been linearly independent. So check back video 2 for more on linearly independent vectors.